Hello, my name is Carlos Busso, and today I'm going to talk about our LAS project improving speech emotion recognition using self-supervised learning with domain-specific audiovisual tasks. This is in collaboration with my students Abinay, Naini, and Goncalves. Emotion plays a crucial role in our human-human interactions. It changes the way that we make decisions. It reflected in our gestures, in our facial expressions, in our speech. Other people perceive that information and make assessments about our emotions, and that dictates the way that we communicate. As we build systems, human-computer interactions, it's important that we take into consideration emotions to build systems that are more engaging. From the perspective of intelligent community, recognizing emotion is very important. We believe that as we encounter a massive amount of data that has to be analyzed, having tools that can potentially identify threatening behaviors is very important. And in this context, emotion recognition is very useful. So when we talk about emotion recognition, it's important to understand what are we talking about? What is the type of descriptions that we were aiming to recognize? First, we can categorize emotions in terms of labels like angry, happy, sad. These are categorical labels that tell us what is categorize the emotional behaviors into these categories, right, that we understand. Additionally, we can also represent emotions using dimensional or attribute-based representations, where we use attributes like to describe properties of the behavior. For example, valence, how positive or negative is the audio. We can talk about arousal, also how calm versus active is the audio, and dominance, how weak or strong is the audio. So these are two alternative ways that we're going to use both in this project. The motivation for our study came from the fact that recently there's been a lot of studies showing that self-supervised models for speech has been lead to improvements in performance that we haven't seen before. They're very clearly better than alternative methods that we used to use in the past. These self-supervised methods are often used generic domain-agnostic pre-text tasks to build the representations from unlabeled data. An example of this is Web2Vec2, which is shown here in the pictures, that use a mechanism similar to a mask language model, where the idea is you mask certain part of the audio, and by using nearby frames, you try to identify the audio or the acoustic properties that is being masked. Again, for this, since you know exactly what you're masking, you do not need labels. So it's very appealing because you can use massive amount of data to train these models. These are has too many parameters, and by using this pre-text task, you can build representations that are very robust. The four most popular self-supervised learning representations for speech are WebLM, Web2Vec, and Hoover, and Data2Vec. These are the four by far more popular systems or representations that have been provided for different tasks, not just emotion recognitions, but also for tasks like automatic speech recognitions, speaker ID, speech synthesis, and so on. So within this context, we asked two important questions. The first one was, how robust are these domain-agnostic representations for speech emotion recognition? In particular, when it deals with cross-domain problems, where you train the data in one domain with one type of data and you test it with a different one. And second, right, whether these models can be improved by using domain-dependent multimodal pre-text tasks. So instead of building something that's generic for multiple purpose, right, we know that emotions is going to be our final task, right? Can we build systems that can be target to emotion recognition? So we're going to go over what we have done this year, right, on these two important topics. So the way that often, right, we build these self-supervised models is we take the model that has been already pre-trained with massive amount of data, and then what we do is to try to fine-tune all the parameters to a particular task. In this case, speech emotion recognitions with abbreviation SER. And the idea here is to use a larger database, right? And the idea is to fine-tune the parameters so it is more in tune to the emotion recognition task. And the third task, right, is once you're done with this, you freeze the model, right? This self-supervised learning framework with models, right? You freeze those parameters so you don't modify them anymore. And this is important because these models are massive. They have millions of parameters. So at that point, you stop that, right? And the only thing that you train is sort of a model that's built on top of that, which is represented here with this green box that's where you train that models to recognize emotions. And here you can also adapt this part of the model to new domains using unsupervised domain adaptations. And we can build this model for categorical emotions or attributes. In this particular study, we're going to look at arousal, valence, and dominance. So in this context, we ask some important questions, right? How important is this fine-tuning part in the model, what we call a step 2, right, which is highlighted here in the red box? How important are these steps in order to obtain good performance, right? How important is to take these models, right, and using emotional data to adapt them to be more in tune for the task that you have at hand? Second, we will looking at within all these representations that have been provided, which ones are more effective for speech emotion recognition. So that's the second question that we have. And third is how adaptable are these self-supervised models when used in a different target domain, right? Here we try to see whether domain adaptations are particularly effective for this task. So we will build the models in one domain and test it in a different one. Since we're looking at unsupervised domain adaptations, we explored two approaches that we have used in the past that have been very effective for us. So we wanted to test it here as well. One is the concept of adversarial domain adaptations. We were going to refer to this as ADA. And the key idea in this concept is that you have a chair representation, which is here represented with these green layers. And then you have two main tasks. One is to recognize the emotions, which is the main task. And the second one is to recognize the domain, whether the data is coming from the training domain, or the target domain, or the source domain. So basically it's coming from where the data that you're training or the data that you want to test it. Because the data, the only thing that I need to know is okay, whether this data belong to, I don't need to know anything about the emotions of that data. This model can be trained with unlabeled data from your target domains, making very appealing solutions. One interesting aspect of this model is that you reverse the gradients, which is again represented by this minus lambda, and then the gradients. And the idea here is that you will find a representation, these green layers, right, that make the domain classifier as random as possible. So when the performance is random, it means that you cannot distinguish between the two domains, and that makes the speech representation very appealing for the task, meaning that the mismatch between the train and test conditions, right, has been minimized. The second approach that we're going to use is the concept of ladder network for domain adaptations. That here is sort of an autoencoder where you have an encoder that is with its decoder, which is highlighted here in this yellow box. What we do is we add noise to the encoder, and we have these lateral connections that connect the encoder with the decoders. And the goal here is to reconstruct these intermediate representations that you obtain within the network. And then we use the bottleneck, right, to predict the motions. So what is interesting about this approach is that when you do have label data, what you can do is to train the reconstruction loss and also the classification task, right? So in this case, you will have both type of losses. However, when you do not have, when you bring the data from your target domain, which does not have labels, you can just use the reconstruction loss. So the models will learn to reduce the mismatch between train and test conditions. So these two approaches have been very useful. We're going to test these self-supervised models with the following settings. We're going to use for training the MSP podcast corpus, right? Release 1.11. This is a very large corpus that has conversations. It has contained over 150,000 speaking turns, and we're going to use arousal, valence, and dominance for these annotations, for these evaluations. The target databases are going to be very diverse. We try 4 of them. The first one is the Nixon tapes database. These are collections that happens during the time of President Nixon. The recordings are very noisy. They have reverberations, they have distant speech. We have annotated portion of this corpus and of these recordings, right? And that's what we use here for the evaluations. We have the MSP Impro, which is collected in a very controlled scenario from active speech. Mockup database very similar. We have English is one of the main benchmark database for emotion recognition, so we use that as well. And we also have the BAN database, which is a database in German. So we have this mismatch on the emotion, on the language, and we also have a mismatch on the emotions, because this database is very biased to negative interactions, while the other ones are not. So there's a mismatch also in the emotional content. And what we found here is that when we tested within corpus, right, we go back to our questions, we see the result here for when we train and test with MSP podcast, right, of course, different partitions. And we observe in this table, you see the columns with L represent the model before fine-tunings, and LR, the columns with LR, right, are the models after fine-tuning. And what we found consistently for arousal, valence, and dominant, we observe that the performance does increase when you incorporate fine-tuning. So we found that there is a clear improvement when using fine-tuned models. When we ask the questions, which representation is better? Well, for the most part, right, the best model comes when we use WebLM. Sometimes Web2Bake gives good performance, but for the most part, WebLM is one of the self-supervised models that give you the best performance. When we tested in cross-corpus evaluations, here are the results for the Nixon tapes. To summarize, we're going to present the result for this database. And what we found here is that when you do adaptations, either with the adversarial domain adaptations or when you use the network, right, you can clearly see massive improvements compared to the models, right, that have not been adapted to the particular domain. So both models are particularly effective. So this table or this figure, that I'm presenting here, it presents the result for the other four databases. And what we look here is for the relative improvements compared to the model when we just train with the models the original self-supervised models that were provided to us. So with the original parameters, without fine-tunings and before adaptations. And what we found here is that for databases that are very similar to the recordings of the MSP podcast, right, you see lower performance gains after you do adaptation. So for example, here you see a small gap for the MSP Improv and the iMockup databases. But when you go to domains that are quite different, right, in language, in emotional distributions, like in the BAM database or in the Nixon state, where you have environmental conditions that are quite different, you will see that there is a huge improvement in performance. The second question that we ask is this idea of domain-dependent multimodal pretect task and how useful is using those for speech emotion recognitions. So the key idea here is that we would like to carefully design a task that don't use label, because we're going to use unlabeled data for training this model. And the idea is to make those very relevant to the problem of speech emotion recognitions. So, and in order to do that, we're going to rely on the relationship that we have seen observed between different modalities, let's say facial expression, text, and speech. Our input is always the speech, and the idea is that by the output or the labels that we're going to use in this self-supervised framework, right, are going to come up with the features derived either from the audio, either from the lexical domain, or facial features. So the idea here is that you have this massive amount of data. You're able to identify labels to train these three tasks that I'm plotting here in these pictures. And what we're going to do next is to build this model or adapt the models, right, with this pretect task. And then we're going to replace those tasks, put the task that we actually need, right, which is speech emotion recognitions. And the hope is that because these models have been trained with pretect tasks that are more in tune to emotion recognitions, right, then the models are going to be more discriminative. So we tested this with different alternatives. So what I'm going to show here is just a summary of what are the things that work best for us during the year. So the first one is related to speech. So what we found is that if our output is the GMAPS parameter set and we try to predict that by using audio. That leads to the one of the best performance. This set is a standardized, the minimal set that has been proposed for paralinguistic tasks. So it's usually used for emotion recognitions, for another paralinguistic task. And this, what we would like to do is again, we build, we take acoustic informations from the system, and we try to predict these acoustic features directly from the representation that we're using. The second task has to do with text. So we're using here a large language model built on Roberta, and the idea is this model, what it does is to do sentiment analysis. So what we do is we take the audio, we look at automatic transcription, we provide those transcriptions to this model, and the model will tell us whether it has, it will give us sort of whether it's neutral, positive or negative sentiment. And we look at the output of these sentiment predictions, and we use that as a classification task. So the idea then, you put a speech as the input, and you try to predict the labels that the text will tell that the model based on text will produce. So basically, we try to predict that performance of what the text-based model does, right, with acoustic features. And the third one is based on facial expressions. The key is very similar to what we did with the text. We built a model that to recognize emotions using facial expressions. We use for that efficient net model, which has been shown to have a state-of-the-art performance on AffectNet, which is another corpus for facial expression recognition. This is for images. And what we do, again, we look at the last layer of this model, and what we do is now we take speech and we try to predict that particular representation. So this is a regression model where we try to match the representation produced by the face model with the representation that you will obtain by using just speech. So the way that we train this is with the MSP face corpus. This is so we have 70 hours of data, right? Some of them is labeled, some of them is not labeled. But what is important here is that we're not going to use label at all, right? We assume that this data is completely unlabeled, and we will use that data, right, to build our model. It has a primary emotion, but as I said, the important thing here is we're going to assume that there's no labels, where we just use this data to train these three pretext fact tasks that we just mentioned. So let's go to some of the results on the crematic corpus, which is a corpus that is also very, very popular in speech emotion recognitions. We observed this is a 6 classification problems where we have angry, happy, sadness, fear, disgust, and neutral as our emotional categories. And what we found here is that if you just use the original model, self-supervised model, or you compare that with the model created with this multitask multi-task pre-training strategy that we propose, we see clear improvement for each of these 4 main models that we have built, right? So we see clearly improvements in consistent performance, showing that these pretext tasks that we're using, right, using multimodalities, are very effective. When we compare the result with the MSP improv corpus, this is again the same corpus that we used earlier, right? It's acted, or these are 4 class problems with anger, happy, sadness, and neutral. We've also observed similar results where we see much better or improved performance for all the self-supervised models when we use the predict tasks that we propose. So this concludes the presentations. I hope that you enjoy and learn what we did during this project. If you have any questions, don't hesitate to send me an email, right? Again, thank you to my students that work on this project, right? And thank you to LAS for supporting our research.